Hello. In this video, we will mention the key points of Chapter 3 for the 11 ASP Mechanics course, which is about work, energy and power. We're going to state the key formulas and we're going to answer a few questions from past AP papers and past ADHS papers. Now, what we need to know is that through the concept of work, we can calculate the energy that it is given on an object. Now, there are two types of energy that we care about in physics in grade 11. Kinetic energy of an object, which is the product of half mass times the velocity of the object to the power of 2. It is the energy of a moving object. And potential energy, we're going to speak a little bit more about potential energy in a few minutes. Now, through the concept of work, we can calculate the energy that it is given on an object. And the main definition of work is the dot product of the force acting on an object multiplied by the distance that the object travels. Now, we need to remember that the dot product of two vectors is the magnitude of vector A times the magnitude of vector B times the cosine of the angle between them. So this means that if we need to calculate the work, we need to multiply the value of the force multiplied by the value of the distance multiplied by the cosine of the angle between the force and the distance. Now, a few examples that we need to know is that, for example, if we know for a fact that the object is moving to the right, so the distance is delta x and the object has a speed v, let's say that we have four forces: the applied force F1, the force of gravity, the normal force, and the force of friction. In this case, because the F1 and the distance are pointing to the same direction, the angle between the force and the distance is 0, so cosine of 0 is 1, so we can ignore the cosine. But for the force of gravity and the normal force, because the angle that they act is 90 degrees, is perpendicular to the distance, then the angle is 90 degrees. This means that the cosine of 90 degrees is 0, so the normal force and the force of gravity in this case do not provide with any work to this object. And the force of friction is opposite to the displacement, so they form 180 degrees. So if we're going to apply cosine of 180 degrees, we're going to find the value of negative 1. This means that friction in general provides negative work. It removes energy from the object. Now, these two laws, we can only apply them when we know for a fact that the force is constant. If we have a variable force, we can say that that the work is equal integral of F times dx, again dot product of F times dx. So maybe again we will need to multiply by the cosine of the angle. So F times cosine of the angle between the force and the distance multiplied by dx from initial position to final position. So more or less this is what we need to know about how to calculate the work. Now, the work is useful because through the concept of work we can find the kinetic energy of the object. So the work energy theorem, which is a very useful theorem, a very useful law that helps us calculate either the work or kinetic energy or mass or final speed or initial speed, states that the total work, the net work acting on an object is equal to the kinetic energy final minus kinetic energy initial. So if we have, let's say, 3 or 4 forces, we can say that the work by the first force plus the work by the second force plus whatever works we have, it is equal to 1 over 2 mv final squared minus 1 over 2 mv initial squared. Now, this is more or less what we need to mention about the work. I think I forgot one important part, that the work, since it is the integral of the force times dx, it means that if somebody gives us a graph of the force with respect to the position, then it is also equal to the area under the force versus the position graph. Now, we have already spoken about the kinetic energy of an object. There is also the potential energy of an object. We probably know that the potential energy by gravity is mass times g times the height from the ground, and the potential energy by the spring force, it is equal 1 over 2 times k times the displacement of the spring to the power of 2, where k is the spring constant. Now, the reason why the potential energy by gravity or the potential energy by the spring is this is because, in general, the potential energy, or more accurately, the change of the potential energy, it is equal to minus the work by conservative force. So it is equal to minus the integral of F times dx. For example, for the spring force, that we know that it is k times x, and actually minus k times x, if we integrate this quantity minus k times x times dx, we find minus and minus cancel each other out, so plus 1 over 2 k x squared, where the x squared over 2 is the integral of x. So every conservative forces are the forces that their work through a closed path is 0, for example gravity or the spring force. Every conservative force has a potential energy associated with it. Now, it is good to memorize the potential energy by gravity and the potential energy by the spring. However, if we need to find the potential energy by any conservative force, we can apply this law. In addition, the reverse, it is true that the force that it is associated with the conservative force, we can find it from minus derivative of potential energy with respect to the position x. So if we need to find if we know a potential energy, we can find the force from the derivative, the opposite of the derivative of this potential energy. So on the potential energy versus position graph, the force will be also equal to the slope of the force versus position graph. Now, there are two important energies that we need to know, the kinetic energy and the potential energy, but their sum is called mechanical energy. And the mechanical energy is kinetic energy plus potential energy. And one thing that is important about the mechanical energy is that if we know for a fact that we only have conservative forces, then the mechanical energy remains constant. So the mechanical energy at one position, it is equal to the mechanical energy at any other position. However, if we have conservative and not conservative forces acting on the system, then the difference of mechanical energy final minus mechanical energy initial, is equal to the work by the non-conservative force, or the non-conservative forces. Non-conservative are the forces that do not keep the same energy, for example, an applied force or the force of friction. Finally, the last thing that we need to know is about power. The definition of power is energy over time, and we need to remember that the average power, it is equal energy or work over time. And if we know for a fact that the force is constant, we can say that the work is equal force times distance. We can assume that the angle is 0 divided by the time, and the distance over time means velocity, so it is the product of force multiplied by the velocity. However, if the force is variable, then we have to derive the work, so the instantaneous power, it is equal derivative of work with respect to time, or work derivative. Knowing this, we'll try to answer a few multiple choice questions and some AP questions and some past exam questions on this topic. Let's start. The first question is about the force that it is acting on an object, and we need to calculate the work done by this force as the particle is moving from position 2 to position 1 meter. So we need to remember that for a variable force, and we know that this is a variable force because it depends on the position x, then the work is equal integral of initial position to final position f times dx. The initial position is 2, the final position is 1, so 4 times x to the power of 3 dx, and all we need to do is enter this in the calculator from position 2 to position 1. I believe this will be a negative work, 4 x to the power of 3 and this is minus 15 joules. Continue to one more AP question. Feel free to pause in order to read this question thoroughly. Basically, what we see is a force that unfortunately it is a non-constant force. It depends on the position x, and also we have an angle theta between the force and the way that the object moves, and we need to find the work done by the by the force as the object moves from position 0 to position d. Now, unfortunately, this question has a little bit of hard calculus, but we can go through. Now, finding the work shouldn't be difficult. It is for a variable force, integral from x initial to x final, f times dx, but since this is the dot product of f times dx and there is an angle between them, we need to also not forget to multiply by the cosine of theta. So we have integral from position 0 to position d. The force is cosine of beta x multiplied by dx multiplied by cosine theta. So we need to integrate the cosine. However, although the integral of cosine is sine, so the integral is sine beta x, if we just leave it like this, it is wrong. So because we need to divide by the beta. This is because of the chain rule of the derivatives. If we just integrate the sine of beta x, we need to remember that the derivative of this is obviously cosine of beta x, but at the same time we need to multiply by the derivative of beta x, which is beta. So the derivative of cosine beta x is, the derivative of sine beta x is cosine beta x times beta. So in this case the beta is missing. That's why we need to divide by the beta to cancel this term. We need to continue and multiply by the cosine of theta, and we need to bring the value from x is equal 0 to x is equal d. Now this is sine of beta times d divided by beta multiplied by cosine of theta minus sine of 0, which is 0, so we can ignore that part, and we're going to select something that looks like this. I think the answer is D, which is the correct answer. We can continue to our next question, which I believe it's not going to be so difficult. And we see that a block is sliding down on an inclined plane, and the work done by gravity is 300 joules. And we need to figure out what will be the work done by the gravity if the block was sliding up. Now, since we have an inclined plane, now as the object is sliding down, gravity has a component that acts on the same direction. That's why as the object is sliding down, the work by the force of gravity is positive, and the value is given 300 joules. If we have the same block, so the force of gravity will be the same, but the object was sliding up, then the work done by the force of gravity would be force of gravity, which is the same, times distance, which is the same, but the angle now is supplementary of the initial angle. Basically, we have a component of the force that acts opposite to the motion. So the work will be the same, but negative 300 joules. We can continue. We are given a force that it is again variable, and we need to find what is the work if we stretch the spring for a distance xo. Now, we remember that the work for a variable force is integral of f times dx, so it will be integral of k times x to the power of 2 times dx, so it will be k times x to the power of 3 over 3, and all we need to do is replace the value of x with xo, so k times xo to the power of 3 over 3, and if I'm not mistaken, the correct answer is E. Let's move on. Now, what we have is an object that it is released from rest, and it slides down for a vertical distance of 5 meters, and later the object is reaching point P, the base of the inclined plane, and probably will slide on a surface that has friction, and we need to figure out how far does it go before it comes to rest. Now, there are two ways that we can try to solve this problem, either with the work energy theorem or with the law of conservation of mechanical energy, including friction. I will try to say that as the object is sliding on the surface with the inclined plane, there is a force of friction. The force of friction is mu multiplied by the normal, and the normal is mass times g. Now, the mass is not given, but we'll see how we can maybe eliminate the mass later. So it will be 0.2 times mass, and the value of g, I will consider it 10 to make my calculations a little bit easier. So the force of friction is 2m, and negative to the way that the object moves on this rough surface. And eventually the final speed will be 0 since the object will stop, and we need to find the distance delta x that it travels on the inclined plane. Now, what we can say is that the work net acting on the object is equal to the kinetic energy final minus the kinetic energy initial. Now, the work net during the whole motion is, as the object is moving down on the inclined plane, the only force that does work is the force of gravity. So it is the work by the force of gravity during the motion downwards, plus the work by friction. However, we need to remember that the work by friction will have a negative value. The kinetic energy final is 0, and the kinetic energy initial is also 0. Now, the work by the force of gravity, it is mass times g times height. And it is positive because the object is moving downwards on the inclined plane. And the work by the force of friction is force of friction times distance times cosine of the angle between the force of friction and the distance. The angle is 180 degrees. So this will be equal to 0. So mass times g times height plus, for the friction we know that it is 2m, the distance is unknown, and the cosine of 180 is negative 1. So we can ignore the negative and just subtract these two, and the value will be 0. We don't know the mass. The g, we said that it is 10, the height it is 5. If I take this to the other side, it becomes positive, so 2m times distance. M and m cancels, and what remains is 50 divided by 2, so the distance that the object travels is 25 meters. We can continue to the next question, which is an object that it is released from rest from a height of 3 meters, and we need to find the kinetic energy of an object as it falls and it reaches a height of 1 meter. Now, in some cases, this is an easy question, but if we are not sure about what we can do in order to answer this, well, one thing that we can do to help ourselves is a diagram. So we release an object from rest, so we know that the V initial is 0, and we know that the height is 3 meters. A little bit later, the object will reach a height of 1 meter, and we need to find what is the kinetic energy. Since the only force that is acting on the object is gravity, one thing that we can do is consider working with the law of conservation of mechanical energy. So we have two positions, position A and position B. So the mechanical energy at position A and the mechanical energy at position B are equal, since the only force is the force of gravity, which is the conservative force. So kinetic energy at A plus mechanical energy at, plus potential energy at A is equal kinetic energy at B plus potential energy at B. The kinetic energy at A is 0. The potential energy at A is mgh at A. What we need to find is the kinetic energy at B, so I don't replace it with 1 over 2mv squared. and the potential energy at P is mass times g times height at P. The mass is 2, the g is 10, the height at A is 3 meters, we don't know the value of the kinetic energy at P, and again the mass is 2, g, and the height at P, which is 1 meter. So 60, it's equal kinetic energy at P plus 20, and this means that the kinetic energy at P is 40 joules. Let's continue to the next question, which is about power. And since we know a function of work, we can say that the power is derivative of work or work prime. So all we need to do is derive this function and later substitute the value of time that it is given. So 3 times 2 is 60 plus 5, and we have the value of 6 times 2 plus 5, so 12 plus 5, 17 watts. And one more question. Feel free to pause this video in order to read this thoroughly. Now what we have is a boat that it is moving with the help of an engine, and this engine generates a power of 10,000 watt, of 10 kilowatt, as the object is moving at a constant speed. And this constant speed is this constant speed is 10 meters per second. The magnitude of the drag force, so it is, since the object is moving with constant speed, there is not only the force by the engine, there must be an opposing friction. The magnitude of the drag force is given by an equation F is equal K times V. And the increase in power needed for the boat to move through is, with a constant speed of 12 meters per second, is unknown. Well, we'll try to figure this out. However, it helps me to make a graph of the situation, make a diagram of the situation. We know that there is a force by the engine. We don't know the force by the engine, but we know that there is a drag force, that it is K times V. And we don't know the value of K, but we know that initially the speed is 10. So K times 10 is initially the value of the drag force. Now, what we know is that the power is 10 kilowatt. The power by the force by the engine is 10 kilowatt. So we can say that since the power is 10,000 watts, it means that the energy divided by the time for this force, or the force times the velocity, the force times the velocity is equal to 10,000. We don't know the value of this force, but we know that the value of the velocity is 10 meters per second, so the force is the force times 10 is 10,000 Newton, so the force by the engine is 1,000 Newton. Now that we know that the force is by the engine is 1,000 Newton, we can use this to find the value of the K, because since this velocity is constant, the F net is 0, and this means that the total force to the left, so K times 10, is equal to the total force to the right, which is 1,000, so the value of the K is 100. Now we have a new situation with most likely a greater force, the force by the engine. I don't know exactly how much is the value, but since we're moving with a greater speed, most likely the force by the engine will have a greater value, and a similar force of resistance, a drag force, that it is K times V. We know the value of K, we know the value of V. The new constant speed is 12 meters per second, so the drag force is 1,200 Newton. And since again the F net is 0, since the speed is constant, the force by the engine has to be 1,200 Newton. Now that we know this force, we can find the new power. So the power, that it is force times velocity, it will be 1,200 multiplied by the new velocity, so the power is 14,400 watts. However, we need to be a little bit careful. The question is not about how much is the new power. The question is about how much is the increase in the power. So the value of the previous power was 10,000 watts. It becomes 14,400 watts. So the increase in power is 4,400 watts. And we can continue with a free response question that has 3 parts. What we are given is a potential energy with respect to position graph. So we can see that the potential energy decreases, it remains constant, increases, and it remains constant again as the object is moving on the x-axis. We are given that the particle is released from rest at the position of 2 meters. This is a little bit important because we can find the kinetic energy 0, and at 2 meters we know that the potential energy is the potential energy is 8 joules. So at the position 2 meters we know that the potential energy is 8 and the kinetic energy is 0. This is important because from the sum of the kinetic energy and the mechanical energy, the sum of the kinetic energy and the potential energy, we can find the mechanical energy. So the mechanical energy is 8 joules, and something that is important about this mechanical energy is that it remains constant. And we know that also this is a potential energy, so the force is conservative. That's why the mechanical energy remains constant. So now we can try to answer part A, which is to find the speed as the object is reaching a new position. Now, what we can do is say that the mechanical energy at the position of 2 meters, it is equal to the mechanical energy at the position of 14 meters, and this is because we have only conservative forces acting on the system, and we can use the law of conservation of mechanical energy. Now, the mechanical energy we have already calculated 8 joules, and the mechanical energy at the new position is kinetic energy plus potential energy. Now, the kinetic energy is 1/2 mass times v squared. The potential energy at the position 14 meters is 6 joules. So we can bring the 6 to the left. 8 minus 6 is 2. It is equal half mv squared. The mass is 0.4 and the velocity is unknown. We can cross multiply. So 4 is equal 0.4 v squared. So the v squared, it is 10, and this means that the velocity is root of 10, or approximately 3.16 meter per second. This was for part A. Now for part B, we need to find the acceleration of the particle when the position is 3 meters. There is no connection between acceleration, potential energy, but we know that there is a connection between potential energy and force. So the force is equal negative derivative of potential energy, and the derivative means slope. So the force is the opposite of the slope. So if we go at position 3 meters and we say now we need to find the slope of this line, so we can say that the force is equal minus rise over run on this line. We can select any 2 points. I will select the start and the finish. Now the line is falling 12 joules, so the rise is negative 12, and the run is 6, so the force is 6 Newton. And from the force we can find the acceleration, because the F is equal to mass times A. The mass was given as 0.4, and we don't know the value of the acceleration, so the acceleration is 6 over 0.4, or 15 meter per second squared. And we can move on to the next part of the problem, which is what is the direction of the motion, what is the direction of the acceleration as the particle reaches the position 3 meters. Well, first of all, it makes sense that, for example, if we had an object that was released from the position of 2 meters and it would be moving downwards because objects tend to move to systems with lower potential energy, just like gravity. So the force, we could say that it is to the right. However, since we find that the acceleration is positive, we can say that the motion, the direction of the acceleration is to the right. So it will tend to move to a position to the right. Again, this is because we found the value of the acceleration positive. And one more thing, because the force is minus the slope is negative, so the force has to be positive. And finally, I think this will be the last part, or maybe not, we need to find the value of the acceleration when the position is 7 meters. So in a similar way, we'll go to the position of 7 meters, and we will say the same thing, that the force is equal minus derivative of the potential energy or minus the slope. But we see that at 7 meters, the line is horizontal, so there is no inclination up or no inclination downwards. So this means that the slope is 0. So since the force is 0, the acceleration is 0. Now there are 3 parts for part D. We need to find, it says that the particle is released from rest at position 2. So we will have in mind that the particle is released from rest at that position. And we need to find the time that the object travels from 2 meters to 6 meters, then from 6 meters to 8 meters, and then from 8 meters to 14 meters. Now you can skip this part if you're studying for energy. This is more related to forces and kinematics. However, we will solve this in the following way. Now, I think that on the first part we found that the force is equal 15 Newton and the acceleration is, maybe I was wrong, the force was 6 Newton and the acceleration was 15 meters per second. We don't need to repeat these calculations. The force was 6 Newton and the acceleration is 15 meters per second squared. And since the object starts from rest and we know that the object travels from position 2 to position 6, it means that the delta x is 4 meters. So for the first part of the motion, we can consider the second law. So the delta x is equal v initial t plus 1 over 2 at squared. The delta x is 4, the v initial is 0, 1 over 2 times 15 times t squared. So 4 times 2 is 8, this is 15 t squared, and this means that the t is root of 8 over 15 seconds, and either we will leave it like this, the first time it is root of 8 over 15, or we can say that the value is 0.73 seconds. Now, for the second part of the motion, from 6 to 8 meters, the object is moving with 0 acceleration, so the object is moving with constant speed. So in order to find the time, we'll use the rule v equal distance over time. Now, the distance is 2 meters from 6 to 8 meters. The distance is 2 meters, but we don't know the velocity. However, we know that the velocity is the final velocity of the previous part. Now, the final velocity at 6 meters, I think we have calculated at part 1. I might be wrong. No, we found the velocity at 3 meters. Now, either we'll use a similar way. Actually, I'm wrong. We have found the velocity when the position is 14 meters. Maybe we'll use this for the last part of the question. However, since we didn't find the velocity, either we will use a similar way, like with the law of conservation of mechanical energy, or since we have calculated the acceleration, maybe we can use the v final is equal v initial plus at. The v final, the v initial was 0 for the first part of the motion, the acceleration was 15, and the time is root of 8 over 15, so the v final is 10.95, so I will consider this 11 meters per second. So we can say that 11 is equal 2 over the second time, and the second time is 2 over 11, which is 0.18 seconds. This is for part 2. And for the last part of the motion between 8 and 14 meters, now first we need to find the acceleration. I don't think we have found the acceleration in that part. We can say that the force is equal to opposite of the slope, so the force is minus. The slope is rise over run. The rise is from 0 to 6 and the run is from 8 to 14, so the force is negative 1 Newton. And from this we can find the acceleration as force divided by mass. The force is negative 1 Newton and the mass was 0.4, so the acceleration is negative 2.5 meter per second squared. Now that we know the value of the acceleration, for the last part we can say v final is equal v initial plus at. The v final is the velocity at 14 meters, and I think that we have calculated this. The velocity at 14 meters, and maybe I was wrong, I think we have calculated in part 1, exactly, it is 3.16 meters per second, so 3.16 meters per second. The initial velocity is the velocity at the end of the 8 meters, which was constant, and it was 11 meters per second. The acceleration we found is 2.5 and the time is unknown, so 3.16 minus 11 and then divide by negative 2.5, the time will be a little bit more than 3 seconds, so the time is 3.14 seconds for the last part of the motion. Now on the next part of the video we're gonna answer a few ADHS exam questions. Feel free to pause the video in order to read the question carefully. However, what we have is a box that it is sliding down on an inclined plane, and we need to draw a free body diagram as it reaches point B of the circle, and then we need to find the speed at point B and the value of the force at point B. Now the first and the last part of the question are related to dynamics. However, the second part of the question is related to the law of conservation of energy. So we'll say that at B, as the object is reaching point B, there will be for sure the force of gravity and the force from the surface, the normal force. So the free body diagram should look approximately like this: the normal force and the force by the gravity. Now, we need to find the speed of the block at point B. One way to find the speed of the block at point B is to say that there is a position A and there is a position B. There is negligible friction, so we can use the law of conservation of mechanical energy. So we can say that the mechanical energy at A is equal to the mechanical energy at B. The mechanical energy at B is kinetic energy plus potential energy, and similar is the kinetic energy plus potential energy for the mechanical energy at B. The kinetic energy at A is 0 because the object is released from rest, and the potential energy at A is mass times g times height. Since we need to find the speed, we will substitute the kinetic energy with 1 over 2 mv squared, and the potential energy at B is mass times g, but the height is equal to the radius of the circle, so mg r. Now, the mass is given, but we can cancel it out. The g is 10, so 10 times the initial height is 1.5. It would be half v squared plus 10 times the radius is 0.5. So 15 is equal half v squared plus 5. We take the 5 to the other side. So 10 is equal half v squared. So the v squared is 20 and the speed is root of 20 meters per second, or approximately 4.5 or 4.6. 4.5 meters per second. And now that we have found the velocity at point B, we can find the net force at point B. Now, the net force will be the combination of the normal force and the force of gravity. So this is the net force, and in order to find the net force, we need to do the Pythagorean theorem of F normal to the power of 2 plus force of gravity to the power of 2, since these two forces act on an angle of 90 degrees. Now the force of gravity, it is mass times g, so 3 times 10, so 30. Now for the normal force there is no formula, however we can see that this normal force is pointing towards the center of the circle. So this is F centripetal, so it is mv squared over r. The m is 3, the v we found it 4.5, to the power of 2 this will be 20, divided by the radius that it is 0.5, so this is 120 Newton. And now that we know the value of the force of gravity and the normal force, we can do the Pythagorean theorem, so 120 to the power of 2 plus 30 to the power of 2, this will be approximately 124 Newton. We can continue to our next multiple choice questions, again from past exams. The question is, how much work is done by the dog when this object is moving for 500 meters at constant speed? So the work by this force will be equal to the force times the distance multiplied by the cosine of the angle between the force and the distance. Since the force and the distance are pointing to the same direction, the cosine is cosine of 0, which is equal to 1. So we can ignore this cosine. Now there's a small problem here. We don't know the value of the force applied by the dog. The only thing that we know is the distance, that it is 500 meters. However, we have a very, very useful part of information, that the speed is constant. And since the speed is constant, the force of friction will be equal to the force by the dog. So all we need to do is calculate the force of friction, which is mu times the F normal. And in this case, the mu it is 0.1, and the normal is equal to the weight, which is equal to 2000 Newton. So it is 200 Newton. And now that we know the friction, whose value is equal to the force by the dog, 200 times 500, 2 times 5 is 10, and we need another 4 zeros. So in total, 5 zeros, so 10 to the power of 5 joules. And we know that an object is initially at rest. It travels with an acceleration of 3 meters per second squared, and we need to find the average power when it comes to a speed of 5 meters per second. Now, we can say that the average power, it is equal to the total work that it is done divided by the total time. Or the force is equal, or the work is equal force times the distance that it travels divided by the time, or the work is equal force times the delta x over delta t, which is the average velocity. However, I will not use that rule because it can be a bit deceiving. The velocity is not constant. So either I will find most likely we need to find the force, and then also we need to find the distance. So what we can say is that the force is equal mass times acceleration. The mass is 10 and the acceleration is 3. So the force is 30 Newton. Now also we need to find the average speed, I think that we can actually say that the delta x over the delta t is equal to the average speed, and the average speed is obviously between 0 and 5. The average speed is 2.5, so force times 2.5, and I believe that the correct value will be 75 watt. However, one more thing that we can do to verify this is find the distance and find the time. Now, in order to find the distance, we can say that the delta x is equal v initial t plus half at squared. Now, this doesn't help us a lot because we don't know the time, so maybe first we'll use the second as the first law of the motion. V final is equal v initial plus at. The v initial is 0. The v final is 5, the acceleration is 3, and the time is unknown, so the time is 5 over 3 seconds, or 1.66 seconds, and from this we can find the distance. The distance is v initial t plus 1 over 2 at squared, so it is 1 over 2. Acceleration, we know that it is 3, and the time is 1.66 to the power of 2. You will give me 1 second for this. The result is 4.17 meters. So the force, which is 30, the distance that it is 4.17, and the time that it is 1.66. So times 30 divided by 1.66, the result again is 75 watt, as we expected with the previous method. Let's continue to our next questions. Well, we are given a potential energy and we need to find the associated force. This should be on the easy side. The force is negative derivative of potential energy. So negative of minus 3x squared plus 2x derivative. So negative minus 3 times 2, 6x plus 2. So the force is 6x minus 2, and all we need is to replace the x with 2 meters. So 6 times 2 minus 2. The result is 10 Newton. We have done a similar question just before. Well, if the work done by gravity as the object is moving down the inclined plane, well, the work done by gravity as the object is moving on the second distance up on the incline will be the exact opposite, so minus 600 Newton. This is because the force is the same and the distance is the same. The only thing that is different is the direction that the force acts. In one way it is the same like the direction of the motion. The second way is the opposite to the direction of the motion. And also we have done a similar question just before. If you want, you can pause the video and try to answer the question yourselves. So if we are 100 meters above the Earth's surface, so at a height of 100 meters, and we release an object from rest, so the velocity is 0, and this means that the kinetic energy is 0. Well, at 10 meters above the surface of the Earth, the kinetic energy can be found by the law of conservation of mechanical energy. So mechanical energy at the top is equal to the mechanical energy at the required position. Kinetic energy plus mgh at the top will be equal to kinetic energy plus mgh at the bottom, or almost the bottom. The initial kinetic energy was 0, so the answer will be m times g times height top minus height bottom, so basically delta h. The mass is 5, the g is 10, and the change of height is 90 meters. And this will be, well, in this case I believe that he uses the value of g as 9.8. If I don't find exactly the same, I'm going to replace the 10 with 9.8. I find 4,500, so, but if we change the value of g with 9.8, we find 4,410. Then we have a box that slides 18 meters before it comes to stop because of friction, and we need to find the initial speed of the box. Now we can use this, we can start answering this with the laws of dynamics and the laws of motion, so with Newton's second law and then with the laws of the three laws of motion. However, I believe that it is a little bit easier to try to use the work energy theorem. We know that an object is moving to the right and we don't know the initial speed, but we know that there is a force of friction acting on the object and the object stops after a distance of 18 meters. So we can say that kinetic energy final minus kinetic energy initial is equal to the work by all forces. Now there's no applied force, the force of gravity and the normal force provide a work of 0, so the only work that we consider is the work by friction. The kinetic energy final is 0, the kinetic energy initial is half mass times v squared, and the work by friction is friction times distance times cosine of the angle between the force and the distance, which is 180 degrees, and this brings a negative work. So negative and negative cancel each other out, so 1 over 2 mv squared, it is equal to the force of friction, which is mu times normal, and the normal force is mg, multiplied by the distance. M and m cancels, so the v squared, it is equal to 2 mu times g times the distance. Now we'll enter all of this in the calculator. 0.3 times 2 times 10 times 180, this is 1800, and the root of this is approximately 32 meters per second. Let me check if I made any mistake in my calculations. So mu, which is I don't know why the mu is 0.3 times g times, I wrote 180 for some reason, it is 18 meters only. So let me repeat my calculations. 2 times 0.3 times 10 times 18, and the root of this is 10.3 or approximately 10 meters per second. Now the next question is a little bit interesting. We have a potential energy that it is a function not only of position x, but at the same time it is a function of position y. And a little bit careful, we need to find the y component of the force at a certain position. Now we know that the force is equal derivative of u, actually negative derivative of u. However, since we need to find the y component, we will say that the y component of the force is equal minus du over dy, which means we derive the function that it is given, we derive the 2x squared y plus 6y, and we derive it only for the variable y. So we will not touch, we will not mix with the value, with the variable x squared. We treat it like it is a number. So this is minus 2x squared times the derivative of y, which is 1, plus 6. And basically the final value for the force y, it is minus 2x squared minus 6. And all we need to do is replace the value of x is equal to and y is equal to 3. Here we only need to replace the x is equal to 2. So 4 times 2 is negative 8, minus 6, it is minus 14 Newton. And one more question for potential energy and speed. We are given a potential energy graph with respect to position, and we know that the force is conservative, so most likely we'll use the mechanical energy at one position is equal to the mechanical energy at another position. Now, the initial position of the speed is at the origin, so at position 0 is the origin, this is our first position, and the final position is where we need to find the speed, is the 7 meters. Now the mechanical energy means kinetic energy at 0, at position 0, plus potential energy at position 0. It is equal to kinetic energy at position 7 plus potential energy at position 7. He tells us that the object moves with a speed of 4 meters per second, so the kinetic energy is 1 over 2 m times v squared. And the potential energy at position 0, we can see clearly that it is 10 joules. The kinetic energy at position 7, actually we're going to find the speed, so we have to replace the kinetic energy with 1 over 2 m v squared. And the potential energy at 7 meters, we can see that it is 8 joules. So playing a little bit with this, we say that 16 plus 10 is equal v squared plus 8. 26 minus 8, it is 18. This is equal to v squared. And if we root, we'll find that the v is equal to root of 18, that it is 4.2 meters per second. We are also given a value for the work given as a function of time, and we need to find the instantaneous power. Since the work is equal to 2.4 t to the power of 3, we remember that the instantaneous power is derivative of work. So 2.4 times 3 times t to the power of 2, so 7.2 t squared, and we need to replace the time with 3.7, and the value is 98.6, so approximately 99 watt. I think these are the two last multiple choice questions before we go to a last free response past exam question. And we have a particle that it is moving with a variable force, and we have done something similar. We need to find the work. We know that the work is derivative from initial position to final position, f dx. We can try to do this without calculator. So 120 times x squared over 2, and replace 0 and 0.5. So 60 x squared, so 60 times 0.5 to the power of 2 minus 0. So 30 times 0.5, so 15 joules. And a potential energy that is given as a function of position. We need to find the value of actually the force that it is associated with this. Now we know that the force is equal to negative derivative of the potential energy, so negative 4 over 2 plus x derivative. This is minus 4 times 2 plus x to the power of negative 1 derivative. So this is minus 4 times, we can bring the value of minus 1 down at the base next to the 2 plus x that has to go to the power of minus 1, so minus 2. And at the same time, we need to multiply with the derivative of 2 plus x, which is 1. So basically, the final answer is minus times minus 4, minus times minus is plus 4 over 2 plus x, and all of it to the power of 2. And if I'm not mistaken, the best answer is E. Finally, we can try to answer this exam question. Now, this is a combination of dynamics and energy. Let's start with part A, where we need to find the tension at the start of the motion. So we have a system of two masses, and we need to find the tension. Now, let me see if there is any friction. Frictionless and massless pulley, and the coefficient of friction is 0.10, so there is friction. Now, the system, the question, I'm not sure it tells us how it moves. Actually, I'm wrong. It tells us that the 15 kilogram mass moves vertically upward, so the other mass will move down on the inclined plane. Now, before we find the tension, we need to do a dynamic analysis of the situation. So we have mass times g acting on the 15 kilogram object. For simplicity reasons, I will consider the g with 10 equal to 10. And there is a tension upwards and a tension on the inclined plane. A tension on the rope on the other side. Also, since the object slides down on the inclined plane, there will be a force of kinetic friction upwards on the inclined plane, and the object is moving downwards because of the horizontal component of gravity, which is mg times sine of 35 degrees, and there is the force of gravity y, which is mg times cosine of 35 degrees, and the normal force equal to the y component of gravity, which is mg cosine of 35 degrees. Now we have to actually do the calculations. The mg cosine of 35 degrees is 45 times 10 times cosine of 35 degrees. So the force of gravity y is 369 Newton, and so is the normal force. And the force of gravity x, it's equal to 45 times 10 times sine of 35 degrees, so it is equal to 258 Newton. Now that we know all the forces, besides the tension, we can first find the acceleration of the system, which is F net over the total mass. The F net is the total force on one side of the system minus the friction minus the opposing force. However, we haven't calculated the force of friction. It's never too late to do that. It is mu times the normal. The mu is 0.1 and the normal is 369, so it is 36.9 Newton. So now we can find the net force as 258 minus 36.9, which is the friction, minus 150, which is the force of gravity on the other side. So we are saying that for the acceleration, we only consider external forces. The tension is, the tensions are forces inside the system, and the normal force is cancelled by the vertical component of gravity. The total mass is 45 plus 15, it is 60 kilograms. Now that we can find the acceleration, 258 minus 36.9 minus 150, and this divided by 60, the acceleration is 1.185 meter per second squared. We can find the tension working on the 15 kilogram object, and by doing F net is equal m times a. The F net is the tension minus the opposing force. It is equal with 15 times 1.185, and this means that the tension is 150 plus 15 times 1.185. The result is 167.8 Newton. Again, this part wasn't related to the part of energy, however, it's a good practice question. Now, we know that this 45 kilograms object is detached from the rope and it is released from rest on an inclined plane. It is the same inclined plane, so there is friction as it slides down. After 6 meters from the point of release, the 45 kilogram mass hits the spring with a spring constant of 320. We need to find two things. First, the speed of the object just before it reaches the spring, and then the distance that the spring is compressed. Let's try to do that. However, in order to do that, we know that the initial velocity is 0, and we need to find the value of the velocity after 6 meters. Now, either we'll use law of conservation of mechanical energy or the work energy theorem. Or, since we used the work energy theorem before in the video, we will use the law of conservation of mechanical energy. So, I have position A and position B, so we can say that mechanical energy final minus mechanical energy initial is equal to the work by the non-conservative forces. Mechanical energy at B means potential energy at B plus kinetic energy at B minus potential energy at A plus kinetic energy at A. It is equal to the work by non-conservative forces. This means work by the friction. Now, if I consider that just before the object hits the spring, the height is 0, then the mass times g times gravity, the potential energy is 0 at position B, and the kinetic energy at B is 1 over 2 mass times velocity squared. We know the mass and we don't know the velocity. The potential energy at A, it is mass times g times height, and the kinetic energy at A is 0. And the work by friction is friction times distance times cosine between the force and the distance, which is 180 degrees, so negative friction times distance. I will not replace the value of the mass, and you will see in 1 minute why. So 1 over 2 mv squared minus mg. We have a small problem. We don't know what is the value of the height at A, but we can use the sine of 35 degrees for this. So sine of the angle, it is opposite, which is the height, divided the hypotenuse, that it is 6 meters. This means that the height is 6 times sine of 35 degrees, so 3.44 meters. And the friction is mu multiplied by the normal force, which is m times g times cosine of 35 degrees multiplied by the distance, that it is 6 meters. The mass is cancelled out, and we know all the values besides the final velocity. So 1 over 2 v squared minus 10 times 3.44 is equal minus 0.1 times 10 times cosine of 35 times 6. Now you will give me a minute to try to calculate this. So from this, I find that the answer is approximately 7.7 meters per second. So the velocity just before we hit the spring is 7.7 meters per second. And now we can continue to the last part of the question to find the distance that the spring is compressed when it comes to rest. Now, I believe that this we will have a few calculations. Let's examine the problem. What we have is an object moving at a speed of 7.7 meters per second, as we found just now, and it comes to collide with a spring that it initially is at its natural length, so it doesn't have potential energy. And as this object is moving down the inclined plane, the spring becomes squeezed, the spring becomes compressed, and the object will come to rest, so the V final will be 0. And we need to find what is this distance that the spring is compressed. One tool that we can use is the law of conservation of mechanical energy. So the mechanical energy final minus mechanical energy initial will be equal to the work by the non-conservative forces, and as we expressed again, the only conservative force is the force of friction, and the force of friction is mu multiplied by the normal, and because we are on the inclined plane, the normal is mass times g times cosine of the angle theta, that it is 35 degrees. We know the value of mu and the angle of 35 degrees, and now we can try to apply the law of conservation of mechanical energy. So kinetic energy final plus potential energy final. However, we have two potential energies. So we have potential energy by the spring and potential energy by gravity, minus the mechanical energy initial, that it is, in a similar way, kinetic energy final, plus potential energy by the spring final, plus gravitational potential energy final, is equal to the work by the force of friction, which is minus force of friction times the distance x. Now, the kinetic energy final is 0 because the object comes to rest. If we consider that at that position the height is 0, then the potential energy by gravity also is 0. So at the end we have only the potential energy of the spring, that it is squeezed, and this is half k times x squared, minus, I wrote final but I should have written initial, so kinetic energy initial, that it is half mv squared, and this v is the 7.7 meters per second, plus the potential energy by the spring. At the start, the spring as it is at its natural length, it doesn't have any displacement, so the potential energy by the spring is 0. And the gravitational potential energy is mass times g times height, and this is minus force of friction times x. Now, the only variable that we need to calculate is the variable x. However, this height is the height from the position that the object is moving with 7.7 meters per second. This is the height, and this is related to the angle theta and the displacement of the spring x. So we can say that the sine of 35 degrees, it is equal opposite, which is the height, over the hypotenuse, which is the distance x. So the height is x times sine 35. So our equation becomes 1 over 2. I need to find the value of k, which is 320. The x is unknown, minus 1 over 2. The mass is given, 45 kgs. The velocity is 7.7 to the power of 2. And again, minus 45 times g times the height, that it is sine of 35. The value of sine 35 is 0.57, so 0.57 times x, and all of this should be equal to minus the force of friction, that it is mu, the mu, if I remember correctly, it is 0.1, so minus mu, which is 0.1 times mass times g times cosine of 35 degrees, and cosine of 35 degrees is 0.82 times x. So we have an equation that we need to solve for x, so the equation is 160 x squared minus, you will give me 1 minute for the calculations, 0.5 times 45 times 7.7 to the power of 2. This is 1,334 minus 45 times 10 times 0.57, it is 256x, and this is minus 0.1 times 45 times 10 times 0.82, so minus 36.9x. So we have a quadratic equation, 160x squared minus, we get the value minus 256.5 minus 256.5 plus 36.9. If we bring that term to the other side, this is minus 219.6x minus 1,334 is equal to 0. And if we apply the quadratic law, the result is 3.6 meters, or a negative value, so we keep the value 3.6 meters. 3.65 to be more precise. Now the last part took a little bit long. It was a little bit complex as a question. However, it is a nice application of the law of conservation of mechanical energy with friction and with two kinds of potential energy by the spring and potential energy by gravity. That's it. Thank you for watching, and hope you have some comments or some inquiries. Feel free to email or comment on the video. Thanks a lot.